At Simio, we're in the business of showing you the future. Our intelligent technology gives you unprecedented insight into complex systems to identify and solve today's inefficiencies and tomorrow's challenges. The Simio solution provides a low-risk opportunity to drive transformational change. Our true digital twin models capture all the constraints, business rules, and decision logic that define the operation of your system. When powered by your data, easily evaluate unlimited scenarios and deliver optimized solutions. No matter what industry you're in, eliminate your greatest operational process and scheduling challenges with a Simio digital twin. See your future success, Simio.
Welcome, everyone, to our November session of our Simio Solution Series. Thank you for attending today. My name is, hold on a second. There we go. My name is Dan Vassalini. I'm the VP of Global Sales over here at Simio, and doing most of the presenting today is going to be Jeff Smith. He is our VP of Training and Academic Solutions. Today's session is how to find the best, in quotes, model configurations using Simio's optimization and statistical analysis tools. Pretty popular topic. We didn't mean to say it for the last one of the year, but it definitely was a well-requested one, and we hope that everyone finds a lot of value in today's session. A few things before we get started here today. Please keep in mind today's session is being recorded for replay purposes. If you'd like to go back and watch this session in the future, or if you'd like to recommend it to a colleague or a friend, just simply go to simio.com. You will see a resource tab at the top of the screen. On that resource tab, the first drop-down is the Simio Solutions Series. Any of these webinars we've done this year and last year, the year before, so the last 3 years of history of our Simio Solution Series are available to watch there. We have a large variety of topics, a large number of sessions we've done. We encourage you to go and take a look and see all the sessions we've done and what's available to you. During today's session, everyone will be muted. If you'd like to ask a question, somewhere on your screen there should be a GoToWebinar dashboard. When mine comes up, it's on the right-hand side of the screen. In that right-hand side of the screen or in that dashboard, there should be a question drop-down. Simply type your question in there, and those questions come directly to me, and I will do my best to ask all questions that come in during today's session. Try to keep these questions in a manner, if they are very relevant to something that's being spoken about, and I can interrupt in a good way, I will do that. If it's more generic in nature, then I'll hold the question until the end. We do try to save time at the end of the session for question and answer. Normally our presentations go about 40 minutes or so, 45 minutes, and then we have a nice 10 to 15 minutes left at the end for questions. So once again, please be interactive. Please type your questions in as we go. All right, so this is the last session of 2024. Before I kind of talk about next year, I just wanted to thank everyone for attending this year, whether you attend live or you are watching this on record. This is the last one of the year. We will plan another series of sessions next year. We'll do the same thing. We'll probably start in the February timeframe, usually leaving December and January off for holidays and the like, and then we'll get kicked off back in February. Once we have a schedule in place, we will definitely get that schedule out there and let everyone know. You will receive the emails you already receive about the solution series as well as the Simio Scoop. It's talked about in there. On the first page, and I'm also going to flash to the last page here, is that QR code. The best thing that you can do for us is scan that QR code. Give us some feedback. Our sessions, obviously, we are more than happy to try to come up with topics for our sessions, but generally the sessions that we do that have the most attendees, the most interaction, the most views on record are ones that are suggested or supplied topics by our customers. So please feel free to let us know what you think we should talk about. If there was a session we did 3 years ago and you went and watched it and Simio has changed over 3 years, and there might be something you want updated in that session, you say, I watched this session and this was great, but this wasn't covered. Let us know. Like I said, we're always looking for suggestions, always looking for anything from feedback on what you think of these sections. So please scan that QR code, give us some feedback, and we will plan our sessions accordingly. With that said, I will turn things over to Jeff here. I will flash both my email and Jeff's email at the end again. So if a question is asked or there's something you want to talk about offline, you will have our information, but I will bring that back up one more time before we're done here today. Other than that, Jeff, the session is yours.
All right. Did you transfer presenter to me? Okay, now I'm presenter. Let's see here. I'm going to show.
As Jeff's bringing up his screen here, we had a slight audio issue this morning before we started. Hopefully the audio is good to go with Jeff, and sounds like it is.
So you guys can see my screen, how to find the best model configuration?
Yes, we can.
And you can hear me just fine?
Perfect.
All right, thank you. Welcome everybody. Let me echo Dan's welcome. Thanks for joining us. Today, what I'm going to talk about is how to use Simio's optimization and statistical analysis tools, as I mentioned in the title, to find the best model configuration. I want to make a couple of notes before I get started. We're going to work through an example model, and the model that we're going to work with is pretty straightforward. It's pretty easy, and you can get most of the way to the best without much work. But the techniques that we're demonstrating are the exact same, no matter how complex your model is. So using a simple model makes it a little bit easier to demonstrate those techniques. And finally, we're in the process of updating our training materials. And the material that I'm covering in an overview today, I'm going to cover in much more detail in our training module on experimentation. And we will go into all of the details of all of the tools that you see here today. And we'll do that in an interactive way in the new training modules. So if this is of interest to you, look for those early next year. Okay, so the example model that we're going to do is a resource allocation problem. So you can see that I have a serial production system that has 4 machines. And what we're trying to decide is 2 basic things. We're trying to decide the capacity of the buffers in between the workstations and the capacity of each one of our 4 processing machines, such that we can maximize throughput and have a profit maximization function. So the thing to look at, I'm going to show the model here in just a second. You can see that workstations A and C are both yellow. What that means is those stations are blocked because we have buffer capacity here, and this one would have a buffer capacity of 5. Workstation A is finished with its processing, but there's nowhere for the entities to travel, so therefore it's blocked, which induces loss of capacity. Same thing with workstation C. And so our resource allocation problem, again, is then to select the number of machines. So in this case, you can see I have 2 units of A and 4 units of B and 1 unit of C and 1 unit of D. So trying to decide what that should be and how many buffer slots I have in these 3 locations, here, here, and here, such that I maximize profit. We also have a physical space constraint that's going to limit the total number of machines that we have. And finally, we're going to have a minimum throughput requirement. So that is our optimization problem. Again, a fairly straightforward problem for our example. And the methodology that we're going to use today that I'm going to demonstrate consists of these 5 things. First of all, we're going to talk about model design for optimization. So how do I design my model to facilitate optimization using the tools? We'll talk about the subset selection tool, the OptQuest add-in, and the brand new scenario generator tool, and then finally the select best scenario add-in. So these are the tools and methodologies that we'll use to solve this example problem. So the first step, again, is design for optimization. I have an optimization in mind. In this case, I want to make my resource allocation decision. So from a design perspective, I want to make sure and use reference properties to represent my decision variables. So my decision variables for this optimization problem are my 3 buffer capacities and my 4 machine capacities. And you can see I've defined those as reference properties. We're going to see this in Simio here in just a second. but that's the first concept of our design for optimization, is to identify the decision variables and then use reference properties for those decision variables. And the second design for optimization is representing our objectives. So in our case, I need to define what it is that makes one configuration better than another so that I can use that to identify the best. And so for my simple model, we're interested in two things. I'm interested in the throughput, which I'm defining as the rate at which I produce entities or produce parts if this is a manufacturing system. And I'm interested in profit. And so in our simple model, we are just tracking the number of entities that leave our system. So that's what this expression represents. The sync1 input buffer number entered represents how many left. And then I'm dividing that by the current simulation time at the end of the model. So that gives me the hourly rate. For my profit, I need to measure a couple of things. First of all, I am assigning a value of 125 for each unit of throughput. So for each unit of throughput per hour that we get from our throughput statistic, I'm assigning a value of $125. That's my revenue. And then my cost for my resource allocation, we're saying that we pay 50 units for each one of our buffer capacity, each unit of buffer capacity, and then each one of our 4 machines, you can see here in my table, has a corresponding cost. And so we apply that profit function, and the throughput expression, we define an output statistic. So to refresh your memory, in Simio, an output statistic is a statistic that's computed at the end of a run. And so when I run my model, at the end of the run, I will have a measure of the throughput, and I will have a measure of the corresponding profit that's based on the throughput that I achieved minus the resource allocation cost. So that is our basic structure of the model. So let me jump over and show this model. So you saw this in the slide. If I just run the model, you can see that I'm in my time plot tracking the throughput as the model runs. And the two components that I talked about earlier, the reference properties that you can see right here, allow me to easily change the configuration. So if I want to go in and say, let's add a 4th machine here and add a 2nd one here, and maybe add 5 buffer slots here, I can easily change those decision variables and then immediately in interactive mode see the net result of that configuration. I can also run in fast forward mode. If I run to the end of my run and then look at my results, and here are the 2 output statistics that we created. So I have a nice, easy way to measure my my profit value, in this case 8566, and my throughput, which is 79.72. So by structuring the model where I have my decision variables that correspond to reference properties, and by defining my performance metrics, my objective function using output statistics, I can easily manipulate the configuration to get the results that I'm looking for. So what we want to then create, instead of running in interactive mode, is that I want to create an experiment. And when we create an experiment, we see that the reference properties automatically become experimental controls, and that we can use our output statistic to define experiment responses. And so in this context of a Simio experiment, a scenario is defined by allocating or specifying values for each one of the controls, and then specifying the number of simulation replications that I want to run. So that's how we're defining a scenario. And then an experiment is a set of these scenarios. So if I go back to my model, for example, and then I go to what I named my baseline experiment, you can see that I've defined 3 scenarios, each with different values for the corresponding decision variables or reference properties. And when I run the model, it gives me an easy way to compare the results in terms of throughput and profit between my scenarios. So back to my ultimate objective is to pick the best configuration. So what I'd like to be able to do is identify the configuration or the scenario that gives me the maximum profit subject to my two constraints. One constraint is on space for my machines, and another is on minimum throughput. Okay. All right, so one thing to keep in mind that's really important when I look at my values here, my throughput and my profit, is these are results of replication. So I am estimating parameters, and because I'm estimating those parameters based on a simulation run, I have sampling error that I have to deal with. And so what I want to do is show how we do that using the subset selection tool. Okay, so I have a specific problem already set up. Let me just grab that. So this is the exact same model. I just set up these 5 scenarios you can see here. And when I run those scenarios, again, my objective is to look for the scenario that gives me the maximum profit. So we'll just let those run. I'm running 10 replications of each of my 5 scenarios. We can see my profit here, and I have my scenarios sorted in descending order of profit. So again, if you just right-click on the column, you can get the sort value. So I'm going to sort in descending order. And so in looking at these values, it looks like scenario 3 is my best profit because it has the highest profit of the 5 that I see. However, as I mentioned, because we're estimating values based on a sample, we also know if we look at the response values, where the little yellow dots here give me that expected value, and the beige bar here gives me the confidence interval around that expected value. So the critical point here is that when I look at my values in the profit and throughput column, these are point estimates. Whereas when I look at my confidence interval, these are interval estimates. So they provide me more information about statistical difference. So one of the tools that is quite useful in this is the subset selection tool. So in order to use the subset selection tool, you need to look at your responses and make sure that you have an objective defined. So for my profit, I want to maximize. For my throughput, I want to maximize. Then I can simply run the experiment and then choose the subset selection. And you can see what it does is it divides my scenarios into 2 different groups. So I have these 2 groups. I'm sorry, I have this group for profit, and I have this group for profit. And in terms of throughput, I have this one, and then I have the other for here. And so what this is telling me is that these 2 are not statistically different from one another, but these 2 as a group are statistically better than these 3, okay? So if I go back to my slide, and what we're using the subset selection tool is to identify these statistically significant differences. And so what you see is a representation of what I just demonstrated, and that the subset selection tool takes your scenarios and divides them into 2 sets based on each one of the individual responses. The potentially best group, so everything in the potentially best group is statistically equivalent, or they're not statistically different from one another. And the reject group, which you can ignore because those are, as a group, statistically different. So the critical part of using the subset selection tool is when I run my scenarios, I can't just look at these point estimates. I also have to look at the interval estimates and do the corresponding statistical significance test. And the subset selection tool will do that for me automatically. Okay, so the subset selection tool designed for optimization and the subset selection tool are the 2 first tools that I wanted to talk about. The second tool that I want to talk about is OptQuest. So using OptQuest is a Simio add-in that I can use to help me with the optimization. And so the optimization that I'm going to solve here is I'm going to specify that my 3 buffers can vary between 0 and 10. My 4 machine capacities can vary between 1 and 10. So these are the decision variables. Then I have, I mentioned before, a space capacity constraint. So if I add up the number of machine A, machine B, machine C, and machine D, the sum has to be less than or equal to 16. So I have a space constraint here. I have a minimum throughput constraint or minimum throughput requirement of 100. And my objective is to maximize this profit value. And so what OptQuest does is it takes that information and then constructs sequentially scenarios in an effort to find that optimal value. So let me pull that up. This is again the same model that we just looked at. I just have the OptQuest preset up to run. So to do that, you just go to select add in here and then go down and choose OptQuest. And you can see right here I have the OptQuest for Simio selected. And once I do that, it introduces a set of properties that we can fill in: the min and max replications, the maximum number of scenarios, confidence interval and relative error, and then the objective type. And then for each one of the controls, it says, it gives me another set of properties saying, should I include this in the optimization? And if so, the minimum value, maximum value, and the increment. So by setting the minimum value to 0, the maximum value to 10, and the increment of 1, there are 11 possible configurations for buffer 1. It can be 0, 1, 2, 3, up to 10. I have the same thing for buff 2, the same thing for buff 3, and for my 4 machine capacities, instead of starting at 0, I'm starting those at 1. For the throughput response, I have the lower bound of 100. And for the profit, we don't have a lower or upper bound. We just have that we would like to maximize that. And then back to my OptQuest properties, the objective, the primary response is profit. So once I have the OptQuest set up, so I have my experiment set up, I have my optimization set up, I can simply click go, and OptQuest, the OptQuest add-in then takes over, and as I mentioned, it sequentially creates scenarios based on previous scenario results in an effort to optimize the performance metric that you specify, in our case, profit. You can see the red shaded throughput are the values that don't meet the minimum. So we had a minimum of 100. So all of these have don't meet that requirement, except for the 119 here and the 112 here. And what OptQuest will do is it will continue to run until one of two things happens, until it identifies or it thinks internally, I have found the best solution I'm going to find, in which case it stops, or it does this maximum number of scenarios. When it does that maximum number of scenarios, it will stop. So I'm going to pause, or I'm just going to cancel that, and I already have this pre-run, so let me just grab the version that's run. And so this is the exact same model if I just let the OptQuest run. And you can see we have the scenarios that you just saw it create. And then down here, if we scroll to the bottom, you can see that it generated 100 different, it generated 100 scenarios. So it didn't come to the conclusion that it was done until it reached that maximum. So the next thing I would do is I would then, as we did before, I would just sort in descending order of profit. And then if you scroll to the top, these are the solutions that OptQuest feels, based on this simple experiment, are the best solutions you have. However, as I said before, we need to make sure that these are statistically different. So if I just run my subset selection, you can see that in terms of our profit, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 scenarios that are in that potentially best group, and all of the rest of the scenarios are in the reject group. So at this point, I can look at these scenarios and say, those scenarios are potentially the best. I'm going to ignore all of the rest of the scenarios, but I can't differentiate based on the experiment that I just ran. I cannot differentiate between any of these solutions. So I can either do further experimentation or just decide that all of these solutions are equivalent in terms of what we're looking for. Okay? So what I would do here is I can then introduce our second tool. So I'm just going to go delete all of these reject values, members of the reject group. Just going to delete all of those, leaving only the scenarios that are in the potentially best group. I'm going to reset that, and then I'm going to use this third tool, select best scenario. So to do that, I've got my scenarios defined. I'm going to clear the add-in because I no longer want the OptQuest add-in, and I'm going to select add-in, and you can see that there are two different select best scenario, one using something called GSP, which is good selection procedure, and a second one using the KN method, which stands for Kim and Nelson. So we're going to do that one. If we choose that one, then gives us a note saying you can't undo this. And so now, instead of having the OptQuest add-in, we have the select best scenario using KN, and you can see that we have its own set of parameters, the confidence level, replication limit, and then something called the indifferent zone. And the indifferent zone is what we specify when you look at two different solutions, and they might be numerically different, but for your purposes, they're equivalent. So if you think about buying a car, and you're going to spend $30,000 on a car, if the car is $30,100, that's probably equivalent to you. So that 100 would be the indifferent zone, or be an example of the indifferent zone. So to run this, I'm going to just set my indifferent zone at 50. And then when I run the model, what the select best scenario does is it runs the specified or the selected scenarios until it can identify the single best, or until it hits its replication limit of 100. So whereas OptQuest created scenarios with different values of the controls, what the select best does is it just continues to run until it can identify either the unique best or until it's exhausted its replication limit. So in the interest of time, I'm going to cancel that and just open the model where it would be had you done that. So I go to model 6. And so if we had continued to run, this is where we would end up. And you can see that the only scenario checked at the end was 097 for our control values of 7 buffer slots, 3 buffer slots, 3, and then for our machine capacities, 3724, and our profit is $15,374. And because the select best scenario add-in terminated with a single scenario selected, we can assume that of the ones that we tested, this is in fact the statistical best solution. And so using that method of OptQuest to identify attractive scenarios, subset selection to identify the potentially best set, and then select best scenario to then take that set and filter it to the absolute best, or the absolute, there can be multiple in the scenarios in the ending set, which would simply mean we can't distinguish between those values. So OptQuest is a very nice tool. I'm going to come back and talk about it here in just a second in terms of a discussion. But before I talk about from a discussion standpoint, I want to show one more tool that is brand new in Simio 18. That is the scenario generator tool. And so to demonstrate the scenario generator tool, I'm going to look at my problem and do a little bit of preliminary analysis. So from our model, we see the processing time associated with each one of the machines. And so we have a minimum throughput of 100. That is one of our optimization requirements. And so using that value, using this 100 value, and then using the processing time, I can take the processing time, the nominal processing time of 1 minute, 3 minutes, 0.6 of a minute, 0.8 of a minute, convert that to a rate. So if I can process, if it takes 1 minute to process, I can process at the rate of 60 per hour. I can compute the processing rate, and then from that, I can compute the minimum number of machines of each type required to achieve my minimum throughput. So I have, in order to achieve the absolute minimum number of machine type A is 2, machine type B is 5, machine type C is 1, and machine type D is 2. I then want to use the scenario generator tool to look at potential buffer allocations around those values. So let me pull this model up again. I'm going to pull up my baseline model, and then I'm just going to copy my experiment. So I'm going to duplicate my experiment, and then I'm going to delete these values. And the first thing that I want to do, I'm going to demonstrate how to use the scenario generator by just looking at the buffer allocation problem. So to do that, I'm going to go back to my model, and for my decision variables, for my machine capacities, I'm going to set those to those minimum values. So we said we needed 2 of A, we need 5 of B, we need 1, is it 1? Yeah, 1 of C and 2 of D. So I'm going to set their default values to the minimum values. Then I'm going to go back to my experiment, and you see, again, this is new. If you don't have Simio 18, you're not going to see this scenario generator. And when I click on that, what it does is it lets me construct a potentially full factorial design based on our decision variables. So in this case, I'm going to do a really simple one. I'm just going to say, I want to look at the buffer capacity. And the buffer capacity I want to look at is between 0 and 5. And I want to have 3 levels in my design. So I'm going to look at 3 different alternatives between 0 and 5. I'm going to do the same thing for buff 2. And I'm going to do the same thing for buff 3. 0 and 5. 3. And for the time being, I'm going to ignore my machine capacity. And you can see that because I'm ignoring those, in my scenario generator, it's using those default values. So that's why I went back and set those default values, so that when I generate the scenarios with my buffer configuration, it will use the default associated with the machine capacity. We can also see down here, we go down here, that the current, it tells me approximately, or a maximum number that it's going to generate. And so we have 3 levels for buffer 1, 3 levels of buff 2, 3 levels for buff 3. So this will generate 27 scenarios. If I just click OK, it's going to generate those 27 scenarios where it's doing this full factorial design, where I have 3 factors, and for each one I have 3 levels. So if I then run this model, I've already run this, so I'm going to skip over to the pre-run version. This is what I end up with. So what this scenario generator has done for me is it said, I want to fix the number of machines at their minimum values, and I want to then vary the buffer capacity around the starting at 0 up to 5. And then again, I'm going to look for the maximum profit value. And I can go and do subset selection. And for this scenario, for this experiment, it found the optimal, just the optimal amongst the ones that I tested anyway, using the just running those 10 replications. Okay. So the next thing that I would do if I was using the scenario generator tool, or another thing that I could do, is say, now that I have found this optimal buffer capacity, 5, 5, and 2, by fixing my capacity A, capacity B, capacity C, capacity D, is what if we use these values as defaults and then let these fluctuate? So I could then reopen my scenario generator, and this time I'm going to turn these off, and this time I'm going to turn these on, and then have these values. I'm going to have these values fluctuate, starting at the minimum value and going up. So I've already done this. I'm not going to show it. I'm not going to show the generation, but I've already done the scenario generation, and this is the result. So you can see that on all of my scenarios that I have my 552 buffer configuration, and what I've systematically varied is the corresponding machine capacities. And so once again, I can go select my profit, do subset selection, and now it is telling me that based on my simple 2-phase experiment, where I looked at different buffer configurations and then secondarily looked at the machine capacities, that this is the best value that I get. Now, some of you are probably asking, why would we do this in 2 steps? Why would I do buffer configuration and machine capacities in 2 different steps? Why not do them all at once? And not surprisingly, I did that. So if I go back and look, if we use all 7 controls, you can see that I have all 7 of them selected. So I have 3 levels of each one of our buffers, and then 3 levels of each one of our machines. And we see here that we are doing generate up to 2187 scenarios. So again, 3 times 3 times 3, or 3 to the 7th, up to 2187 scenarios. So that is a lot of scenarios that get generated. They have a big space to do. And when I did that, of those, 702 violated the space constraint. So we had that space constraint that said cap A plus cap B plus cap C plus cap D has to be less than or equal to 16. So 702 of the 2187 violated that constraint, and so they weren't generated, but left 1,485 scenarios to be evaluated. If you look at my little runtime down here, you can see that I ran that on my laptop computer, and it took 21,266.4 seconds. For those of you who can't do that kind of arithmetic in your head, which I certainly cannot, that's 354.4 minutes, roughly 6-7 hours of compute time for me to do those scenarios. So for a problem like this, that's probably not a practical solution. However, if we were to do this in the cloud and had access to, say, 1,000 cores versus the 8 cores or whatever that I have on my laptop, then we could easily do this within an acceptable time. So while this brute force method of saying, hey, let's generate everything and pick the best one, not practical on a computer that doesn't have a lot of cores, but definitely practical if we have a lot of cores. So this is something to keep in mind when we're using this scenario generation tool, is that if we have access to cloud computing, lots and lots of cores, one solution is to just use the scenario generator to generate a whole bunch of scenarios, and then let the experimentation filter out the best of those. So I did that again, and it ran pretty slowly, but it does find a very good solution, because our 2-phase approach used the 2 separate optimizations, one on just the buffer capacity with fixed machines, and then the second one on machine capacity with fixed buffer, which doesn't give you the same level of coverage as doing the full experiment. So the process that we went through is as follows. Back to the very beginning, the title of my presentation was Finding the Best. Build the optimization-friendly model. In our case, we want to make sure that we have reference properties for the decision variables, because that facilitates this type of experimentation with our automated tools. And experiment responses for the objective function, so that you can do the evaluation, again, with the automated and semi-automated tools. Once I have my optimization-friendly model, I want to identify a set of potentially good scenarios. We looked at 3 ways to do that here. One is manually. I could just guess, and for a relatively straightforward optimization like the one that I'm doing here, manual works pretty well. You can zero in on this one pretty well. OptQuest is going to work a little faster and be a little bit more comprehensive for you. And Scenario Generator is also quite useful. Scenario Generator is a tool that you can do some course evaluation, and then you can do more detailed evaluations. It's a very flexible tool for finding this potentially good set of scenarios. Once I've done that, regardless of whether I do it manually or with OptQuest or the Scenario Generator, I can then use subset selection to identify the set of potentially best scenarios. This is the dividing your set into our potentially best set and our reject set. And then from the potentially best set, I can use one of the 2 subset select best scenario add-ins, either KN or GSP, to identify the best, or if it can't find the best, the set of best, the subset of the best from the set that you give it. Also note that I have several feedback loops here. It's a typical experimentation phase that is not linear. You don't just start out with your model and end up with the best scenario, but you typically iterate around a few times. If you think about our experiment using OptQuest, for example, one simple way to use OptQuest is to use wide ranges of values like we did, zero in on an attractive set of scenarios, and then to rerun OptQuest by tightening up those bounds. So you'll note again, when we ran OptQuest, we totally ignored this minimum throughput, right? So we could have computed the minimum throughput and realized that we can't ever have less than 2 of machine A, or 5 of machine B, and 1 of machine C, and 2 of machine D, but we didn't do that. So in OptQuest, we just said, hey, start them at 1 and go to 10. And so as a result, when we ran OptQuest, we saw a whole bunch of the configurations that ended up with that red shading because the solutions didn't meet the minimum requirement. So one of the options would have been to do some preliminary work or some screening work and then come back and then re-optimize using OptQuest with these newly found bounds. So once again, it's not a simple run one time and be done, typically an iteration between several of these tools. So that was what I was going to present today. And as I said, this is a very high-level overview. We're using all of this material, this exact same model in our new training materials, where we go through in detail all of the tools that you just saw, all of the options, what all of the parameters mean, how to use OptQuest effectively, how to use the scenario generator effectively, what are the differences between our subset selection, or our select best scenario tools, the KN tool, and the GSP tool, and so on. So all of that is going to be covered in our new training materials, which, as I mentioned, you should look for at the beginning of the year. So with that, I promised Dan I would leave some time at the end to answer some questions. So I am happy to do that, Dan, or Kiara, if we have any questions.
All right, perfect. Thanks, Jeff. Yes, we tons of questions that came in here. We'll see how many we can get to. I'm going to lump the first set of questions together because you just kind of talked about it, but I want to just make sure it's very clear as far as the answer is concerned. So the lumping of the questions is, what's the difference in the algorithm between OptQuest, GSP, and KN? And then at the same time, does this scenario generator, why would you use this in lieu of OptQuest, and the scenario generator, in essence, make OptQuest redundant at this point?
Sure. I will do what I can to answer those. First of all, if you take OptQuest and scenario generator as one set and the select best scenario as a separate set, these are two different things. OptQuest and scenario generation creates different scenarios, right? So OptQuest creates them using an optimization, an internal optimization. Scenario generator generates them using a factorial design. So their function is to create scenarios, whereas the select best add-ins take a fixed set of scenarios and choose the subset that are the best. And so in terms of the algorithm, the difference between GSP and KN, a little bit technical to get to, but the references are in the help, and you can see the original papers. But in general, GSP tends to be more effective if you have a large number of scenarios.
Okay, perfect. All right, let me get into the meat of the questions, and we'll see what we can get to, and then we'll put our emails up at the end in case we don't get to someone's. All right, when running multiple replications of different scenarios, is the theory behind identifying statistical significance of each scenario the same as finding the p-value to test a null hypothesis? As a mouthful.
Yeah, so let me pull up one of our models here. Let's see our manual subset selection model, and I can look at my response results. And if you look, what subset selection found was that scenario 3 and 4 are in the group that are potentially best and the other 3 are not. So from a statistical standpoint, it said these two are not statistically different from one another, but as a group are statistically better than all 3. So one way to think about this is a sequential paired t-test, where you're just doing a direct comparison, saying, is this one better than this one? No. Is it better than this one? Yes. Is it better than this one? Yes. And so that is, if I'm understanding correctly about the question, that is what it's doing. It's just looking at the p-value and making a statistical statement about, is this statistically different from that, using that hypothesis test.
Okay. All right. I think this question is.
But again, let me just echo one time that this is really important, because again, we have a very simple optimization here, and so it's really kind of simple to see the difference. But in the general case, it's not all that easy to find difference. And so you want to make sure that you go through and do that appropriate testing before you make decisions based on the results.
Okay, thanks. I think this question is in kind of a similar line, but let me bring it up just to make sure. What's the best way to determine the right number of replications? Will the confidence interval shrink indefinitely as the number of replications increases? In essence, how do we ensure we're not p-hacking by running too many replications of a single scenario?
Well, I mean, sure. So if I go here and say, okay, well, let's jump this up to 100 replications and then run it, and then I can go back and look at that in the at the response value. Certainly, when it starts running, you're going to see that you're going to see a couple of things. First of all of the parameters that we're estimating move around. Okay, so that's the idea that what you see in the table is really just a point estimate, and when you run more experimentation, you get different point estimates. But yeah, you can see that the confidence interval is narrowing. The more replications I run, the more likely the confidence interval is to narrow. From a statistical standpoint, the more replications I run, the narrower the confidence interval will get, and the more confident I am in the estimate of this value. In terms of whether that's just p-hacking, so in other words, I'm just running a lot to try to get a better p-value. I mean, that's the whole idea of doing this kind of testing, is that I am estimating a value, this little dot value. I'm estimating that value from a sample, and if I increase that sample size, I'm becoming more confident about my estimate.
Okay.
So there's no general idea of saying, okay, here's how I decide how many to do. It comes down to what's the level of confidence that you want to have in your estimate. If this is a very important decision, I want to be confident, so I'm going to run more.
Got it. Okay. All right. The ultimate question that always comes out of these type of sessions, and it came up early, and I held this question a little bit here. Does OptQuest find the true, quote, optimal solution?
So before I answer that, Dan, I think I ignored the second half of one of the questions you asked, where they asked specifically about scenario generation versus OptQuest, and does one make the other obsolete? So let me address that first, and then I'll come back to that notion of true optimal. And so no, it doesn't. So they do two different things. So once again, what scenario generation does is it generates a potentially full factorial. So it would be full factorial in the absence of constraints, right? So it's generating all of those values. So if I'm running a model and I'm doing some preliminary experimentation and I want to do a very coarse experiment of saying, let's look at a minimum value, a maximum value of all of my decision variables, scenario generator is my tool, because prior to the scenario generator, you would just do that manually. I would say, okay, suppose I have one buffer and 5 buffers, and one buffer and 5 buffers. You would do that manually. And that was really the impetus of doing the scenario generator tool, is that as a normal part of experimentation, this is what we do, so let's automate that. And because you can select the individual controls to use, you have very fine control over what actually gets generated. OptQuest, on the other hand, is an optimization tool where it is sequentially using results from the previous scenarios to try to identify, a good region of the feasible region to try to find the optimal value. So it uses proprietary algorithms internally that we don't have access to find good solutions. So OptQuest has been shown to work pretty well over a big variety of different problems and optimization problems. Now, to the question of does it find the true optimal, it doesn't good solution. It might in fact find the optimal, but it doesn't find the guaranteed optimal.
Jeff, start your answer again there, please. Please, your audio cut out for like 2 seconds. So start your answer again, please.
The answer on OptQuest and true optimal?
Yes, true optimal.
Okay, so OptQuest does not find the guaranteed optimal because you have no way to prove it. It's not a provably optimal solution. It finds a good solution in general, and it might in fact find the optimal, but it doesn't find the provable optimal. So for example, if I look at my optimization problem here, if I have 11 options for each one of my buffers and 10 options for each one of my machines, and I ignore this constraint, that's somewhere on the order of 13 million configurations. So I have 13 million configurations, right? We don't quite have 13 million because we have this additional constraint. But remember, when we run OptQuest, we said maximum number of scenarios 100. So I did 100 scenarios of those 13 million, approximately 13 million, right? And so it can find good solutions, and sometimes it might find the optimal, but it can't find the guaranteed optimal unless you run all of the potential scenarios.
Okay, so unless you're running 13 million, you're not getting the optimal solution, basically.
It's not quite that straightforward. You might be getting the optimal solution. You can't get the provably optimal solution. So I might have the best, but I can't guarantee that it's the best.
Got it. Okay. All right. Let me check timing here. We'll go two or three more questions here, and then we'll wrap up and we'll put the email back, or put the slide back up with our emails just in case. Is there a simple way to run sensitivity analysis with OptQuest or Scenario Generator?
Scenario generation would be the easier of the two because you could run, what scenario generation is going to do is it's going to create the scenarios that let you do the sensitivity analysis. So if, in other words, if I want to see how sensitive my throughput is to the buffer capacity in the second machine, for example, Scenario Generator will generate the scenarios to let you do that sensitivity analysis. It doesn't go back and do the numerical analysis, but it creates the scenarios that facilitate that analysis. OptQuest is not really set up that way to do that kind of sensitivity.
Okay. All right. How do you know how many scenarios will be generated by the Scenario Generator?
So when you run Scenario Generator, as you see right here, what it does. So if you look here, I have 3 levels, 3 levels, 3 levels, 3 levels, 3, 3, 3. So it's saying 3 times 3 times 3 times 3 times 3 times 3 times 3. That's what you get right here, 2187. So if it did the full factorial, there would be 2187 scenarios. But in this problem, I have the constraint that cap A plus cap B plus cap C has to be less than or equal to 16. And so there were 702 that violated that constraint, so that led to 1485. So at pre-calculation, when you set these values, it can't determine exactly how many it's going to generate unless you don't have constraints.
Got it. All right, let's go with one more. Let me pick it off the list here. Actually, let's maybe do two more here. When using OptQuest, how do you decide on the min, max, and increment values for the controls?
Okay. Let me pull up an OptQuest one. This is our ready to run OptQuest version. So we look at the min, max value. So as I said here, in this one, I just did a really broad sweep, right? And so I just did 0 to 10, 0 to 10, 0 to 10. And for the machines, I did 1 to 10, 1 to 10, 1 to 10. Okay, so I did no pre-computation at all. I just said, hey, let's just take a broad stroke, and did that. But as I also mentioned, it generated a whole bunch of scenarios that didn't meet our minimum requirements, which if we had looked at that before and had known, okay, you can't solve this problem without a minimum of 2 machine A's and 5 machine B's and so on because of the raw capacity, I would have tightened up those bounds. So if I tighten up those bounds, the bounds here, instead of going from 1 to 10, I go, from 2 to 10. In this one, I need to have a minimum of 5. So if I tighten up those bounds, what I'm doing is I'm reducing the overall size of the solution space, and so I'm ostensibly getting better solutions. Or OptQuest is going to have an easier time of finding a good part of the feasible region. Okay, so that really comes down to how much time do you want to spend pre-computing, trying to decide what those optimal values for the min, max, and increment are, and how much time do you want to just let OptQuest chug away, using kind of the brute force method.
Got it. Okay. All right, we will wrap there. There's just a couple of lingering questions here. Let me grab control back real quick here and just share our email addresses again, just in case. All right, you should be seeing, hopefully, nope, there's our email addresses there again. Also the QR code. So just to wrap, if you weren't here at the beginning, QR code, please scan that, give us some feedback. We're looking for any type of suggestions for 2025 solution series. Any type of recommendation you might have, you can put in there for us and let us know. Also give us feedback on how today's session went. If you have any questions that weren't answered today, anything that you didn't get a chance to type in, or perhaps one of the lingering questions that didn't get asked, feel free to reach out to us directly. You see my email address and Jeff's email address is right there. You can reach out to us and we'll get questions answered and addressed back to you. Otherwise, as I said at the beginning, this is our last session here of 2024. Thanks again for attending in 2024. We look forward to doing these again in 2025. Everyone have a good rest of your year, and we'll see you again in a couple months. Thanks, Jeff. Goodbye, all.
Thank you, everybody.